Um, so let's start with magnetic flux. It's just like electric flux. So phi b is defined as integral of b dot dA, and it has units of Weber, 1 Tesla times 1 meter squared. So it has the same story like the electric flux. For example, if you have, let's say, uniform magnetic field, and let's say it's acting on a surface that is tilted by an angle theta. Let's say this is the area vector, and it's tilted with respect to this. Let's say this is theta. Are you following? Then flux will be simply, the magnetic flux will be BA times cosine theta. Okay? So that brings us to Gauss's law for magnetism. Gauss's law for magnetism tells you that as far as experiments show, integral of B dot dA is 0. Because there are no monopoles. Yes, no monopoles observed. Okay, remember, in the case of E dot dA, do you remember what it was?
Q over epsilon.
Yes, Q enclosed over epsilon 0, but there can be no Q enclosed in magnetic case because cannot be, but no such thing has been observed yet. It always comes in pairs. All right? Okay, now we can talk about magnetic force on current carrying wire. All right. So here we imagine a wire, and this wire is carrying a current. So let me just I'm taking a bit of this wire dl, and there's a current moving in the same direction, and there is a magnetic field. So let me start from what I already know. Force is equal to Q times V cross B. And this was the case for the force felt by charges moving with a certain velocity. Isn't current also some charges moving with a certain velocity? So we can rewrite this like this. dF, the tiny bit of force felt by the tiny portion of charge, is this. So I'm going to rewrite this as dq over dt times v times dt cross b. Yes? Did you follow this? I just multiplied and divided by dt. So what is dq over dt? I. And v dot dt, v times dt is dl, right? Velocity times tiny bit of time is dl cross b. So that's how we get df, the tiny bit of force felt by the tiny portion of wire carrying current is like this. Okay? When you have a uniform magnetic field and straight wire, then you can just write it like this. You can just simply write F is equal to IL cross B. This is for uniform wire, uniform B field, straight wire. Okay? Does it make sense to you? So let's look at an example. I have an inclined plane. Okay, this inclined plane has an angle of theta, and on top of this inclined plane is a wire carrying a current, let's say I. Okay, and this wire has a mass m, and the length is L, all right? Plus, there is a magnetic field pointing down. So far, do you understand the geometry? The question is, if this wire is at equilibrium, then what is the current in terms of everything else? Do you understand the question? Yes? Let me just draw it one more time and I will tell you. So this is the inclined plane and there is a current coming out, right? There is a magnetic field pointing down. Okay, and this wire is at equilibrium. If it's at equilibrium, then what is the current? In terms of everything else, like in terms of B, in terms of L, in terms of mass, etc. So first of all, is there gravity? There is mg. Which way is the magnetic force?
Actually, this here, but normal from the plane.
Normal from the plane. So
Cosine part, let's say, there will be actually cosine, sine, and
So, by the way, it's the same story. Like any cross product, you can use your right hand. So you start with L and go to B. Okay. By L, I mean the direction of current. So it's going out, right? And magnetic field points down. Do you see it? So it's pushing to the right. So, do we agree that force is pushing in this direction?
Can you demonstrate it again?
Sure. Let me draw it on the board. So, current points in this direction. Current is this way, right? Magnetic field goes down. I cross B F is this way. Do you see it or not? Or let me just point. I goes this way, B goes this way, thumb goes to the force. Everybody? Yes? Good. So we need to find a balance here. To find the balance, we need to also account for the third force, which is the reaction force N. So all these three must be at equilibrium, right? Let's concentrate on this direction over here. Over this direction, we don't even take into account normal force. Somehow normal force is equal to the sum of this F and the sum of this mg cosine theta. No, sine theta, right? mg cosine theta. F sine theta. Very good. So what we care about is mg sine theta, which is pointing in this direction, right? Must be equal to F cosine theta. Everybody agrees with this? Yes? What is F? ILB. Why there is no sine theta at the end? It's perpendicular. B and I are perpendicular, right? So I have mg sine theta equals to ILB cosine theta. I is mg over LB tangent theta. Okay? Okay, very good. Do you have any questions at this point? No? Let me ask you another question, another example. So I have a wire that it starts like this, bends like this, and then finally bends like this. So these parts of the wire are in the same plane. This is perpendicular to it, okay? And I have a magnetic field pointing in this direction, and there is a current on this wire flowing like this. What is the total force on this wire due to the magnetic field? Let's start from the unnecessary part. I already gave you the answer.
Zero.
This part.
Zero.
The force on that part is 0. Why? L and B are parallel. They are actually opposite, but still.
You call them parallel in mathematics.
Yes, exactly. So, they give you 0. Then I can just draw this like this and put my magnetic field in. And this is the current. Now I have to deal with only two pieces. And the left piece is still easy. What is the force? So let me say this is 2r. Let's say this is also 2r. So what is the force due to this part? I times 2r times b. And with what is the direction? You are saying that the direction is up and you find it by,
Right.
so I goes like this, right? B goes like this, thumb points up. Yes? So this is the force. Let's call it F1. 2 IRB. How about F2? Because of the rest. We need to integrate, but after we integrate, we will find something interesting. It's not 0. It's something else that is, but you have good intuition that things that are interesting are 0. That's also nice. Okay, so let me start from here. Let's call it theta, right? And you are claiming that there is symmetry. We will see. So this is your L, right? This is your DL. And which way is the force? Radially outwards. Excellent. This is your DF. And the magnitude of DF is B times I times DL. Do you have any objection to this? No. Okay. Why there is no sine theta? They are perpendicular everywhere. So, as you mentioned, because of the symmetry, for each such element, for each element over here, there is an element over here that would have a force in this direction. So this will cancel that. So we are only interested in Fy. Do you agree? What is dFy? df sine theta. So B times I times sine theta times dl. What is dl? RD theta. Everybody agrees with this? Do you have any questions? No? Fine? Good. Good. Then F total is just the integral of this. So B I R sine theta d theta going from 0 to pi. Yes? And in
Where do we start?
Where do we start? We start here. We go all the way here. Right? BIR sine theta. What is integral of sine theta? Minus cosine. So I have BIR minus cosine theta evaluated at pi and 0. And I get 2 BIR. As you can see, the force due to this one is also 2 IRB. So it's the same. And the total force is 4 IRBs. But what is interesting is that the straight wire having a length 2r and something that is bent have the same force.
Yeah, but the forces, are they in the same direction?
They are in the same direction. They are in the same direction. So we sum up the forces. So what's your concern is
F1 is upward, F2 is like out of the...
no. Look, F1 was up, right? But F2 was combination of all these things, all these forces that were pulling up. But when you sum them up, it is a single force pointing up. Okay? Okay, good. So I want to talk about torque on a loop of wire. Okay. In this case, I'm imagining, first of all, an axis. Let's say this is the main axis. And on top of this axis, there is a loop. Okay. This loop has an angle of theta with this plane. And there is a magnetic field in that direction. Okay, this is the magnetic field. And finally, there is a current on this loop. This side of the loop is A, the other side of the loop is B. So far, did you miss anything? I hope you didn't. So let me ask you, what is the force on these sides? For example, let's start with this side. What is the force on that side?
IBL sine theta.
IBL sine theta. Very good. IBL sine theta. There's a minus sign because of negative sine theta, right? But as a magnitude, that force is IBL sine theta. But tell me also, please, the direction.
On the axis of rotation.
Axis of rotation, out or in? He is saying out, right? So why it is out? Because I start with current that is pointing this way, right? And I go all the way to B. So it's out. Maybe I should show it like this. So it's out. Do you see it? So F over here is out, and its magnitude is IBB times sine theta. How about the other side over here?
Same magnitude, opposite direction.
Same magnitude, opposite direction. Does everyone agree? That's easier to show. I goes like this, B goes like this, F goes like this. Did you manage to do it?
Can you show it again?
Sure. B part. I goes like this, right? B is in this direction, so F is like this. Good. The same magnitude, IB times B times sine theta. Will these forces create any torque on this loop? No, they won't. They cancel each other, not only as a force but also as a torque, because like they act on the axis of rotation, so they won't create any torque.
But they create but cancel, right? They don't.
They don't create at all, because they are on right on top of the rotational axis. Okay. How about the other sides? For example, what was your name? Sorry. Onat. Can you find the direction of force on top wire? So I goes like this. You shouldn't use left hand. I goes like this. B goes like this, right? F goes up. So F is pulling it up over here. So this is 90 degrees. Of course, it's confusing because we are trying to imagine 3 dimensions in 2 dimensions. Similarly, here B is like this, I is like that, I cross B is pushing it down. All right? So what is F for these ones? IBA.
Sine 90 law.
Exactly. Times sine 90 degrees is 1. So it's just I times B times A. Right? And also here it's I times B times A. Do these forces create torque? Yes, they do. Right? And to find their torque, we can imagine, we can just extend, actually this is, can just extend it like this. So what is this distance? The arm of force is, you see, this is B over 2. This will be B over 2 times cosine theta, right? So the torque that you have from one of them is I times B times A times B over 2 times cosine of theta. But since there are 2 forces here, this one is trying to rotate it this way. This one is trying to rotate it that way as well. So there are 2 of them. Here is the counterintuitive part. Which way is the torque? Do you remember that torque also had a direction? R cross F, yes. So
This direction, F is in this direction, so in this direction.
isn't it along the axis of rotation? Yes. So
Ben böyle gözüküyorum ama şeye göre yanlış çizilmiş.
okay. Okay, so torque is in this direction, right? That is the direction of torque, which corresponds to a rotation like this. Let me draw it again. This corresponds a rotation like this. So far, are you with me? Yes? So torque is equal to I times B times A times B times cosine of theta. Well, we took this theta, right, over here. What if we took the other side of theta? Do we call it complementary angle? Yes? Which complements to 90 degrees. So, I'm trying to draw, it's very hard now to draw on top of this. So, if I draw an area vector pointing down, okay. This was theta, right? So the area vector is pointing down, and this is alpha. Alpha is pi over 2 minus theta. So cosine theta is sine alpha. Do you agree with this? Yes? So look what happens. Tau is I B A times B times sine alpha. So let me rearrange stuff here. Tau is b times a times b times sine alpha. No.
I am başlayacak.
Okay. Did I do anything wrong? Not yet. And I won't do anything wrong, don't worry. So, is this the area of the object? Yes. So you see torque is B cross I times the area of the thing. Do you see it? Because it brings out the sine alpha, and sine alpha comes out when you have cross product. Let me draw it again. So I have an area vector pointing in this direction. I have a magnetic field pointing in. No. I have a magnetic field pointing in this direction. Area vector pointing in this direction. Which way was torque? Torque was out of the plane, and I made a mistake here. You see, since torque is out of the plane, just has to be this way. Okay, because A cross B is pointing out. All right? Are you confused? No? Good. So we have a special name for this. We call this magnetic dipole moment. And you can see why, right? You can see why, because it just acts. So mu, magnetic dipole moment, is defined as I times the area of a loop. And as you can see, it's mu cross B. And you can compare it to electric dipole moment, in which case it was P cross E. Do you remember? This was electric dipole moment.
Biyoloji laboratuvarının kapısı kapanmamış oldu.
Let's stop here and have our quiz.
Alarm çalacak.